Assalamu alaikum students, today is the lecture number 2 and we will study what is a floating point representation, floating number representation, and then we will study the decimal number representation and the scientific notations, what are the significant figures, and then the error analysis. So first of all, we will study a floating number representation. So why it is used? It is used to represent the number with a larger numbers or larger quantities, larger basically range of numbers, and a very small range of numbers. Like if you have a very big number and you cannot write it in simple ways, a larger number of digits, so you just represent in the form of 2 or 3 digits, and that is the significant digits. And also if you have to write something like in the millimeters or nanometers, so you have to use for a representation of the smaller numbers, you have to use this kind of significant digits or floating number representation. So the basic representation of this or scientific notation of this floating number representation is R equals to M into B to the power E. So that is basically a very general representation. M represents for mantissa, or we also called as a significant, and B is the base. That is normally in the decimal number system we use the base as 10, and also in E is represented as an exponent, that is power. So the term floating represents floating point, refers to the fact that the numbers or a decimal point can float, or it can be placed anywhere relative to the significant digits of the number. So if it is shifted, if the decimal point is shifted to the left, then we add the numbers in the power of 10 and in the decimal representation. And also if we shift the number to the right, then we represent the number base 10, the power of or exponent of the base 10, in the form of a negative number. So this is all about how to write the significant digits. So the floating decimal point representation is of the form R equals to plus minus M into basically a decimal representation is in the form plus minus M into 10 to the power E. So that has the base 10, and where M is 0 point, D1, D2 to so on dk, where dk is in any number between 0 to 9, and D1 must not be equal to 0, and the exponent has the range lies between minus 100, minus 99 to plus 99. So the number representation and the significant digits. Alright, now for to write the number in significant digits, we use a method or a certain a procedure or a certain criteria, and that is a chopping and rounding. Whether you have to truncate, basically to truncate the number, you have to either chop it off or round it off. So in mathematics we use the technology of rounding. So what is a chopping? What is the difference? I will tell you the difference between a chopping and the rounding. So there are two ways of terminating the number of the k digit decimal machine number: approximating. So this significant digits or significant number is represented like this. So it is chopped off. I want to chop it off up to dk. And I want to skip that dk plus 1 and dk plus 2, so on. So chop means just cut it off. Just cut it off and write the number as it is. So if I chop this number up to dk, then the scientific representation of that number becomes 0 point, d1, d2, so on dk, 10 to the power e. It doesn't matter that the dk plus 1 is whatever the number is. So this is chopping. And rounding is a slightly different technique or advanced technique we use in mathematics, and that is if we want to just chop it, if we want to terminate this number up to dk, then we use the rounding technique. That is, if we have to observe the dk plus 1, and notice that if dk plus 1 is greater and equal to 5, then we add 1 to dk before chopping. and if the dk plus 1 is less than 5, like the chopped number. So this is all about the rounding, and I hope that you already know, already have the concept about this rounding. So it's better to use rounding instead of the chopping in this numerical analysis. In this numerical computation subject, you have to use the rounding technique, and the rounding off is more accurate than the chopping. Alright, so this is all about the rounding and chopping. If you have any questions, you can ask me in the online session or in the class. Now we come to the point of the error analysis. Now we analyze how many types of errors are there. So first of all, we have to represent the errors. That if one is our calculation, basically we have two solutions, two type of solution. One solution is called the exact solution or analytical solution or actual solution or true solution or true value, and the other one is represented as the numerical solution or approximated solution or measured solution or approximated solution. I hope that you got my point. So this is our true calculation, and one is our true calculation or actual value, and the other one is the approximated value. So first type of error is the absolute error. Absolute error is basically it is, remember that error cannot be a negative number, so we always write it in the mod form. Mod means absolute. Absolute means that any negative number and a positive number turns it into the positive number. So errors cannot be a negative quantity. So we write it absolute of the true value minus the approximated value, or the approximated value minus the true value or actual value is basically the absolute error. Okay, now we come to the point of the relative error. That is the second type of error, and it is basically the quotient of the absolute error. That means absolute of true value minus approximated value, or approximated value minus true value. That is absolute error divided by it is basically the quotient of absolute error and the actual value or true value. So it is all about that, and also along with the denominator must not be equal to 0. So true value must not be equal to 0. Mod of true value must not be equal to 0. So this is a relative error, and also percentage error is very comparable to this relative error. Percentage error is all about this relative error, and we just have to multiply with 100 and to get the percentage error. So in many experiments of physics and chemistry, you have done this before, the percentage error. Okay, now the third type of error is the round off error, and a round off error is a very common error you have to face in each and every method in the numerical computations, because this is the imprecision. This is caused by the imprecision of using the finite digit arithmetic in practical calculations, just because of the floating point numbers. For example, in first calculation, I use, if I say I have to mention tolerance in each and every method. So tolerance is basically the standard form of tolerance is up to 4 decimal places. That is 10 to the power minus 4, 10 to the power minus 4, or 10 to the power minus 3. So if you don't truncate the number for about 4 decimal places, then or if you don't round it off, then you will face the problem of the round off error. And if I would say that you have to use the calculations, you have to use the tolerance up to 2 decimal places, and you don't consider it, and you just consider the values up to the 6 or 8 digits, then it will definitely arise to the round off error. So this is all about the in the computations and in MATLAB you will face this problem, the round off error. Most common cause of error is this imprecision. Okay, so next one is the truncation error, and it is truncation error is caused by the approximation in the computational algorithms itself. Basically in the Taylor series this error arises, and you will study this in the finite difference approximation, that up to if I use this in Taylor series, you know that there are terms, and if I consider the terms and just up to the 4 terms are considered, then the 5th one arises to the effect of the truncation error. And basically the concept is that the more terms are considered, chance of probability of having the error is less, error is reduced. And also error is reduced by second way, and that is if you reduce the step size, then error is reduced. Otherwise, if you just assume the first 2 terms, then third one is the error of, that says the size of the error or order of the error. So also more terms are used, error will be definitely reduced. So this is all about the truncation error, and we will study in the finite difference approximation. And then we have to study modeling errors. Okay, modeling error is all about that. I have to tell you this the fact that if I want to solve some problem of the real life, so we can first of all convert the real life problem into the mathematical model. That is a very basic kind of technique. So just construct the model in the form of mathematics. Just construct the real life model, convert it, transform it into a mathematical system. So this is the first step, and what you have to do, you use the techniques of mathematics. If it is or if it is a differential equation, then you use the techniques of the ODE, ordinary differential equation, and then you solve it by these exact or analytical methods and get the solution. Now what you have to do, you just convert that mathematical solution in the form of a real life solution. So that gives the solution of the real world problem or real life problem. So this is basically the cycle of solving the real life problem. Okay, so modeling error arises if you construct the mathematical model, and you have the real life problem and you construct the mathematical model that is not accurate up to the real life problem. Like you cause the errors in the construction of the mathematical model. That is, let me explain this. For example, you have certain parameters or certain restrictions or constraints that affect the real life model, and you don't construct or develop the model according to that. You skip some kind of parameters, you skip some kind of conditions or constraints, and then you solve the problem. So you will not get this problem solved, and you cannot relate it to the real life solution. So this is all about the first step lies in the first step of the model. So that is errors in the construction of the mathematical model. Simple is that you are not able to construct a real life problem or to transform a real life problem into mathematical model perfectly. Okay, so this is all about the modeling errors. Okay, and simple is that if and also in the mathematical model your mathematical problem is not well posed. So it's ill posed, and you know that ill posed problem can be transformed into well posed problem by using a suitable substitution or transformation. I told you in the well posedness. Okay, so it can be sometimes model problem can be further simplified in order to compute the solutions. Okay, so this is all about the modeling errors. Okay, next one is the data errors. Data errors. Okay. There are errors because of the entry in the input data. Simple is that. So basically major of physical experiments generate such errors because you have to collect the data in a raw form, and sometimes the input data is not valid according to the given domain. That arises to this data error. For example, you have to take the sample of the average age of your class, and the average sample, I would say that of your class is between the range is between the 18 years to 24 years, and if I enter this like 54 years, then it is out of the domain. So that will be my data error. Also the height of your class. The average height of your class is in between 4'10" to 6'2" or 6'3". So if I enter that like 7-1, so that is out of the case, out of the range. So that develops its data errors and it affects your solution. So that is all about the data errors. And also the last one is the logical error, and logical error is a very common error. Basically, you have to keep in mind logical error is all about the human error or blunders in the implementation of the program or code. For example, it is also a computational error. So it is due to the human. Like if you have to enter in some kind of a condition in a programming, you have to enter greater than, and you just enter, you do the blunder and you just enter the less than symbol. That arises to the logical errors. So this is all about the types of the errors. Major errors are just like these type of errors, and there are many various errors that generates and that gives the solution not accurate. So for having the solution to be accurate, you just have to use this, that your errors, these all type of errors depending upon the nature of the equation or any function, you just have to reduce the error. If the error is reduced, method is accurate, efficient method, otherwise it is not. So this is all about errors. Okay, now I am using the word again and again, accurate, accuracy of a method, accuracy of a method. So why don't I use the term precise or prescient? So let me show you what is the difference between a prescient and accuracy. So what is a prescient? You have studied in the first year or in your intermediate level. So what is the difference between a prescient and accuracy? So prescient is that how close the Mayet values are to each other. So the Mayet values are to each other. That means a solution is precise because they are relatable to each other. The Mayet values, approximated values are related to each other. So that means it is a precise. These all are precise values. This is all about the prescient. But the accuracy is that how close a Mayet value or your Mayet values or experimented values are to the actual value. So that is the targeted value or a central value, and close to the ideal situation. So if you have many experimented values, that must be equal to the your ideal solution, that is closely related to or closely related to, basically related to your actual or true value. So ideal solution basically. So this is accuracy. So we will use here accuracy, not a prescient. Prescient is also preferable that your Mayet values are must be close to each other, but it must be close to the ideal solution. So these are the examples. Sometimes if the values are far to each other, then we say that far to each other. So that means in the first diagram you can see that you have low prescient and low accuracy. And also sometimes the Mayet values are close to each other, but they are far enough from the targeted value. So that means that is high prescient and low accuracy. Okay, now next case is that sometimes your Mayet values are not close to each other, but they are close to, they are far enough from each other, but they are close to the target. That your solution is not precise, prescient is low here, but accuracy is high here. And sometimes your Mayet experimented values or approximated values are close to each other and also close to the your targeted value or ideal solution. So that means high prescient, high accuracy. That is ideal case of any experimented value, any method, any technique. Okay, so this is all about the prescient and accuracy, and there is also one more example just left for the exercise. So if you have any questions, any queries regarding to this, then you will ask me. And also in the next lecture we will start our proper methods, and we will start it from the numerical solutions to the nonlinear equations, that is from the bisection method, and also we will study the basic commands used in the MATLAB. So you have to install the software of MATLAB on your systems, because in relating to each and every method we will implement it in MATLAB. So we will study the basic commands, how to have some kind of information about the MATLAB. So